Well, thank you for coming. I'm David Ehrenpreis. I'm the director of the Institute of Visual Studies, which you are sitting in. As you know, as you probably know, it's a multidisciplinary institute of people who are working across the campus and working with things visual. Every semester we have exhibitions and other door.
Hey.
And we're actually going to have an exhibition next week, which you'll be getting emails about as well, which is the course that's been meeting this semester, which is a design course. Some of the students are actually in this very room. Not to put any pressure on them. And every class we have multidisciplinary courses. We also have Colloquia, and that's what you're sitting at. And we'd like to have faculty and guests present on their own work. And this time, we have them about 3 times a year. This is our last one for this year, but there will be more coming up next year, so you'll get those visits as well. Our guest this time is Roger Thelwell, who's from mathematics. We're happy to have him here. And so he's going to talk about, I should say mathematics, a visual feast, kind of the visual aspect of mathematics, or the mathematical aspect of vision. So I'll leave it with that to Roger.
Sure. I just wanted to thank all of you for coming today, and for David Ehrenpreis and Daniel for inviting me to give a talk. So you might be a little worried here as you see this slide. I did this all in a real math setting, so in a slide environment. And I was working so hard to get some kind of like a chaotic system or some kind of nice fractal in the background here, but I just couldn't get the fonts to work. So this is supposed to have a beautiful, you can just, if you can close your eyes and imagine the flyer with this beautiful fractal image. That's what I had here. It was a Julia set, so a beautiful symmetry, capturing a lot of really interesting systems and interesting and iterated math system. But so my name's Roger. I'm in the math department. I've been here for, I guess, 4 or 5 years. I like to study water waves, so we'll hit some of that stuff at the very end. I was trying to I have much more information, much more to talk about than I have time to talk about today. So I'm going to, as I was building the slideshow, I was trying to I kept putting things in. So it's only a 20-minute talk, and I had 60 slides. So I cut. So I'm down to 20 slides, so that means that I'm cutting out maybe some of the things that you're here to see. But I've tried to put in just a flavor of some different ideas. So kind of tracing the mingling of mathematics with art, and then some of the more recent things where we're using visualization to try and get some pictures about some mathematical ideas. So both as a teaching and as a research aspect. So, okay, so it all started Euclid's Elements. So this was circa maybe 300 BC. So the kind of the birth of modern Western mathematics. And I'm probably freaking you out now, but I have this equation. This is the only equation in the whole talk. Okay, so what this is, so Euclid, the original way that people thought about mathematics was very visual. So there was a description in this kind of seminal mathematical text, the first mathematical text that we have record of. And so it has the Greek translation and then an image here. And it's a little hard to see, so we can blow it up. But what this image is telling us is that in modern algebraic terms, it's telling us, well, we can think about x's and y's. That's representing some kind of area. So if we're able to think about this image, really this image and the image after this capture this algebraic statement. So what Euclid was able to do is, although he didn't have the way of writing, he didn't have this algebraic notation, he did think very visually. And the entire Euclid's Elements, it's a nice book, a nice text with 13 sections talking about a variety of topics dealing with algebraic constructions. So let me just quickly talk about this, and that's about all the math that I'm going to do, is in order to interpret this thing, you go back a slide, Dan. So we take this side as the side length x, and this as the side length y. So this x times y is this quantity. So what's this? Well, the little blue square is this quantity x minus y over 2 quantity squared. And then forward a slide. And then this is the quantity x plus y over 2 quantity squared. So if we think of this as x and this as y, then this is x plus y. We cut it in half, and we get this x plus y squared. So you can go through with a lot of these things and kind of do a visual argument about these algebraic statements, which is quite interesting. Typically, people think of Euclid's Elements as constructions. Constructions building squares and rectangles and triangles. But we're really interpreting them in a different way, in this visual way. And that was kind of a novel thing and a way of formalizing the logic and writing it down well. And actually, I've been teaching a class for the last 2 summers, or the last summer, and I'm teaching it again, where we're doing this actually in Greece. So, okay, the next slide for this. Okay, so then we come to the Renaissance, the High Renaissance. Leonardo da Vinci, this Uomo Vitruviano. So this was the Vitruvian man. And so this is kind of the blend of, we're now moving into kind of looking for these beautiful shapes in the human form. So kind of drawing out this kind of beautiful mathematical symmetry that we exhibit and formalizing it and thinking about proportions and forms. So this is a classic image, and it brings in these kind of beautiful kind of classical forms of the circle and the square. Okay, next slide. So in the high school, Raphael. So it's a little hard to see in this image, but I don't know if you can see there's a little blackboard here. This might have been Euclid down here in the corner, Euclid or Archimedes, giving a little presentation. I think this is actually supposed to be Raphael, a little self-portrait that he stuck in the luminaries. But really this image is to show you the effect of kind of this idea of perspective, this one-point perspective that we have. And constructing this mathematically, you can often see the perspective and the strong use of perspective in the High Renaissance images. So it's this blend of mathematics and capturing perspective in a very lifelike way. Next. Okay, so now Hogarth, this was in 1750s. Hogarth made a parody of this perspective. So next slide. So here's an engraving. So this was an engraving actually in John Kirby's Linear Perspective pamphlet. It was a pamphlet from about 1750. And in this engraving, Hogarth makes all of the mistakes of the artist that he saw around him. So we can see back here, here's a man on this far hill lighting a who knows what from this woman leaning out of the window. Here we've got a lot of weird kind of perspective things. Here's a boat that's giant back here, all sorts of things here. Here's things in the wrong perspective order, things that are close are small, things that are far away are large. So there was really this kind of an unschooled idea about perspective at the time. So artists were copying the masters, thinking about what the perspective, trying to follow their methods of perspective without really understanding the mathematics. So actually a famous mathematician, Brooks Taylor, of the Taylor theorem, wrote a really great pamphlet, although it was virtually unreadable by the artist. He wrote this in the early 1700s. And it was actually a layman's interpretation of this, John Kirby's, in the 1750s, that Hogarth illustrated this for, and actually Kirby became quite famous and became a royal teacher of perspective at the time. So this was the parody of what Hogarth saw as he saw around his fellow artists doing the kinds of mistakes they were making with perspective. Okay, next. Okay, so that was kind of the parody of the impossible object. Well, here was Penrose. This was in about 1950s. So Penrose now had a very nice stylistic impossible object with this twisted beam object. And so Penrose, some of you might have heard Penrose tilings, Penrose triangles. Penrose was very much influential in a famous artist, Escher. So we see Escher's relativity from 1950s, and we see the same kind of twisting structure that we see in the Penrose triangle. Okay? So Escher wasn't formally trained as a mathematician, but he's probably one of the most famous mathematically influenced artists that we know. So he takes these designs, and all of you, I'm sure, are aware of Escher. And if not, you should look him up and look at a lot of these things. But he does these impossible cubes, impossible triangles, the Penrose triangles. And he's also very interested in tiling. Very interested in tiling. So next slide. So here's one of his famous tiling problems. He was involved with, you can think of tiling as a sheet of paper on it. We call it the Euclidean plane. So you can tile this, a complete tiling, these different shapes that fit together that would cover the whole plane. So that's a standard tiling. And Escher was heavily involved in the early days doing these kind of tilings on the Euclidean plane. But he was also interested in the hyperbolic plane, representing an infinite plane in this way. So what we have is, we can kind of think of it as a Cartesian plane, but as we get farther and farther from that 0 point, all of these points kind of correspond to what we call in mathematics the point at infinity. So we're stretching. We can imagine it wrapped around a sphere almost, or on the inside of a sphere. And as we come up, it's getting either, we can go this way, it gets farther and farther away from us. So this is a similar kind of perspective issue, but in a different type of geometry. So the artists typically before Escher were thinking in this Euclidean plane. Escher moved beyond into the hyperbolic plane. And this is an example of some tiling, some tessellations, and then this kind of nice hyperbolic type feature on the edge. So the distances out here are getting, so a measurement in here might be 1 unit, but out here the measurement of 1 unit would be very, very small. So we have this nice kind of hyperbolic representation. And then my buddy, I went to Burning Man in 2005, and I was at University of Washington at the time, and involved with a lot of guys in the math department who really liked mathematical art. So this was one of the installations that was out on the playa. So it's this dry lake bed with a bunch of cracks all around. So there's a kind of a beautiful mathematical structure in this drying clay in the clay bed, all these cracks and fissures. And then this was this really nice installation of a section of the hyperbolic plane. And what this is, what the hyperbolic plane is that we can imagine if we have a disk. We can build that through hexagons, through 6 equal pieces, and build around. But now, what happens, 6 equilateral triangles? What happens if we stick a 7th equilateral triangle in it? That thing that was a plane before, that was perfectly flat, now buckles. That's exactly what this is. You can see, here's a section, what would be a hexagon built with 6 equilateral triangles. 1, 2, 3, 4, 5, 6. Oh, there's one more, 7. So this is a buckled plane. And at every point, it buckles in the same way. So it has this hyperbolic, it has this curvature built into the surface. So we can imagine this. Escher realized this as his disk, that the central limit, in stretching the edges. If we imagine this as a rubber sheet and we were stretching it, we could pull kind of all those wrinkles, and as we pull it, they kind of get, if we change the distance metric, they become less and less looking like a buckle. So we're able to kind of stretch out the sheet, moving kind of all the wrinkles, all the difficulties to this larger, smaller and smaller scale. So this he called hyperbolic immersion, and so this is, I think, kind of like a 3-dimensional Escher type vision. We see the same kind of tessellation patterns. This is actually a tessellation or tiling of the hyperbolic plane. So it's not an accurate, it's not a perfect representation, but it's a pretty good representation of a chunk of a hyperbolic surface. Okay, next one. Okay, and then this is another friend of mine Fritz Overmeyer. I think some of you have met him. He's a logician, was at Carnegie Mellon, real wild guy, giant head of hair. This is some visualizations that he did in OpenGL as an undergrad. I was a grad student at the time. He was coding away. He was doing these incredible kind of fly-through graphs, really. And they're Cayley graphs, representing actions of Coxeter groups, finite Coxeter groups. So there's a lot of mathematics wrapped up in here. And you can imagine if you're looking at these objects, mathematicians often want to look for symmetries. What this is really an object that lives in not now the second dimension or the third dimension. It really lives in the fourth dimension. It lives in something we call S3. Well, this is a projection from S3 into the reals, into R3. So we've got this point at infinity that Esther represented on the ring of his picture, on the ring of his images, as kind of this center point of this orb. So the graph becomes increasingly complex as you move in. And actually, the software I have on the web here, you can actually fly through all of these objects. So you can fly through, you can swell these things. You can do a lot with the objects. But what's interesting about this is, so this is some Coxeter group. This is actually somebody that Escher ran into and was trying to learn about this hyperbolic kind of surface. This, again, is like a hyperbolic manifold. So this idea that Escher had, I think, has been taken by a lot of kind of people in the mathematical arts community and used, and they're kind of growing on Escher's ideas, expanding this to higher and higher dimensions. So this is the Coxeter Group. And there's a link if you want to see any of this stuff. Okay, next one. Okay, so now that's some of these nice images where we're representing more mathematical type objects. Well, physical objects also capture a lot of mathematics. So here's a couple of pictures. These are some images of some double bubbles. So just soap bubbles. And what do we see about them? Well, they look to be fairly symmetric. They have this nice, strong dividing line. That's a membrane in there. And it turns out that if we think about a bubble as this perfect mathematical object that tries to optimize, tries to maximize volume while minimizing surface area. So it's this kind of min-max idea. It wants to contain as much as it can with the minimum amount of surface. And that's what bubbles do. So as a mathematics problem, that's a very interesting problem. And that's a mathematics problem that we can visualize, a problem that's maybe we can't solve mathematically, but the soap knows how to solve it. So we get some insights, some mathematical ideas from the surfaces that we can build. So people do these things. They build square bubbles. They build all sorts of things. They bend wire and dip it in and look at minimal surfaces and think about how these can change from one thing to another. So there's a lot of interesting kinds of things that can come out of soap bubbles. So there's the physical kind of soap bubbles, and then there is here's a real mathematical construct. It's called a torus bubble. What is it? It's a double bubble. It's got a ring like a donut, and then a dumbbell through the hole of the donut. And I don't know if anybody's been able to make this thing. I suspect it's pretty hard to construct something like this. But I don't know. I mean, I've been looking at a lot of YouTube videos in the last week, and I wouldn't doubt if somebody has done this. Okay, next slide. So I mentioned that the Burning Man was in this dry lake bed, all these cracks and fissures. And I don't know if you've looked at any kind of patterns like that before in the soil, but you'll see a lot of times a crack will start, and then it might split into two, and then it splits again. So that's what the soil's doing as it experiences these stresses. When it experiences too much stress at a point, it's like an earthquake. When it experiences too much stress at a point, it cracks, and these cracks then spread out. So it's exactly the same thing bubbles are doing. Bubbles are trying to minimize somehow this energy, and they're splitting. Bubbles split in a different way, and they're splitting in a higher dimension, but they split just like a crack would in a clay pan. So the ideas that we're getting from bubbles, we can apply to crack formation. We can do a lot of things with very simple experiments and get some mathematical insight about them. So yeah, there's some really cool experiments that people are doing. Okay, now this is, because I build myelin in the abstract, this is something now, this is now a mathematical image, really, of a very physical object. This is something she calls wave field. And to me, when I look at this, I study water waves. I see crescent water waves. I see a wave train. It's these lines of waves with, I see a transverse instability. I see that wave train breaking up, going two different directions as wind blows from this direction. So it blows, and I get a breaking in the front. So this is a common pattern that you see in the ocean. You can come up with solutions to it. You need a little bit of damping on the surface of the water. But I was actually working at Penn State at the wave tank there, and we were making these things. So you see these things, and then I saw this sculpture, and I was amazed that I was always used to seeing this kind of in the dynamic surface. And I suspect if she had been able to do that, she would have done that also. But this is a pretty striking, for me, a pretty striking image. And how the light changes on it through the day, I can imagine could be really, really beautiful. But this is a giant earthwork. Okay, next. And then that is pretty much it. I just have a bunch of links with some other ideas. Some of the interesting things, so there's the ripple tank, and I'll start a movie in just a minute. But there's a ripple tank where you can actually go in and play with stuff, so you can get an idea of how visualization can help you think about things. There's all these cool non-Newtonian fluids things. Cornstarch on a speaker that forms all these fingering kinds of things. So thinking of the math of that. Ferrofluids are awesome. It's oil with a little, oftentimes copier ink put in there, and you drive a magnet and you get all these great shapes. E8, have you guys heard of this? The super simple group E8. This is the surfer dude's theory of everything. So he has a grand unification theory. And that's focused on a Coxeter group. Well, not really a Coxeter. It's this super simple group, and he's looking at the symmetries of that. So he's spinning it around the super high dimensional group, looking for symmetries in that group, looking how particles interact. So he's able to pull all his interactions from this group E8. Impossible objects, this is a guy in Japan, a mathematician who builds these ramps that look like they should go downhill and they really go uphill, or vice versa. So a lot of cool things there. Air rings, this is somebody sitting in the bottom of a pool blowing air rings. You see vorticity at work. And Smale's paradox, that's a differential topology problem. That's if you have a sphere, how do you invert it? Can you twist that sphere inside out in a differentiable way with a differential map? So that, for us mathematicians, means that it doesn't have any sharp edges in it. So there's a lot of cool things. Do any of these things seem interesting to look at? Or I have perhaps the next one, which is the Mobius transformation. So Daniel, could you pull that up? That is on the web now. And I'll just leave this going, and you can hit this with full screen. Yeah, so this is the Mobius transformation. And I'll just leave that. And if you guys have any questions, I could take them while this is playing.
Where could we get those citations so we can look at them?
I'll have this posted. So yeah.
This will also be on JM YouTube, and all of those links, you can access all the links from the actual YouTube video of this presentation with you in the front row.
And so let me just describe a little bit what this is. This is an idea called a Mobius transformation. This was one of the best mathematical images, they said, in 2007 or something. But it's talking about doing things mathematically, algebraically, to quantities. This is an inversion. This is taking a set of space, a space in Cartesian space, and saying 1 over that. What does that look like? Here's a transformation with a dilation, an inversion. So it looks fairly abstract here, but the beautiful thing about this film is that it's so well described by a very simple transformation into the third dimension. So if we think of this as what's called a stereographic projection of the sphere with the object on the sphere, all of those actions in the Mobius transformation are simple actions of the sphere. That's our translation. Dilation. It's our rotation. And we have a big inversion coming up. Vroom. So that's it. So that transformation that you saw at the beginning is exactly this, but with the third dimension added, so you can see what's happening. Okay, that's it. Thanks. Yeah.
A two-part question. One, why is it that fractals lend themselves to modeling natural structures so well? And part two, how much does the idea of the golden section that say figures so prominently in the sacred geometry like cathedral building, how much does that prefigure the development of fractal geometry?
Well, so I don't know a whole lot about fractal geometry, let me just say that. But what I do know is that for me, fractals are I think of construction as a very basic tool. So fractals are kind of a constructive way, we say iterative way of building things. So if we have these very simple things that an organism can do, if it can remember to turn right, left, right, and do that repeatedly, then it's generating a fractal. So these ideas of the golden mean, these are coming out of, we can see it in a logarithmic spiral or something in these seashells. The nautilus shell is typically where you might see this. And it's doing something repeatedly and just doing it over and over again. So the idea of this fractal nature, of this fractal thing, is saying, let me understand this, what looks to be a very complex process, but let me break it down into the simplest kind of operations I can and just do them repeatedly. So do something really easy millions of times rather than try and understand a part of the system completely isolated from another part. So we need a kind of a more global picture of something in this kind of fractal structure to put it all together. But it's really all based on this one construction and just letting it flower, letting it evolve. I don't know if that answers your question, but that's maybe the best I can do. Other questions? Yeah, Phil.
The kind of graph you're talking about, is it Coxeter?
Coxeter.
Coxeter.
Famous Canadian mathematician.
And you showed an image of it, and you said that it was, as I recall, 4-dimensional, and you said that you had some way of going inside of it and looking at it. Could you
yeah, that's really hard to explain.
I was going to ask you, can you explain that to
so,
me?
but let's think about going from 3 dimensions to 2 dimensions. We can think of that as a projection, right? So if we have this sphere that lives in 3 space, just like these Mobius transformations, we're shining a light through it and we see its shadow. Okay, so things that would appear straight on that sphere, like kind of great circle arcs, as they project down, they become curves. So we're getting a glimpse of this higher dimensional by projecting down. So how would we view a 3D object? We could imagine these 6 faces, put it in a box, and shine a light through each of the 6 faces and see what it is. That's what we can capture. So that's what the book Flatland was about, right? They're trying to see third dimension. And then there's a book called Sphereland, actually, that is often produced in a back-to-back printing with Flatland that steps it up a dimension. So we have a really hard time imagining the 4th dimension. I imagine it as like some kind of color or some kind of tonal change as I move through.
Is it always a product of light?
No.
Oh, no.
No. I mean, this E8, I don't remember what dimension E8 lives in, but it's like 20-something. String theory, this new modern theory, really what they're saying is that we kind of envision 3 space dimensions and a time dimension, but really what's there, there's these tiny little dimensions that shake, stuff's going on, but they're on like a millimeter scale or micrometer. We can't see them, but we can pick up those interactions. So it's the same kind of thing, but dimension is tough for us. That's a really hard concept to get. There's some nice visualizations of hypercubes, which is a higher dimensional cube. You can imagine a cube. If you think of a cube, at every vertex, every point, we have 3 faces coming in. Well, let's add another face to that. That's what we have to do. And
easier said than done.
Yeah, easier said than done. Any other questions?
Got one for you. You began your talk with an interesting visualization of the equation. It reminded me of the Pythagorean theorem and
Exactly.
the corresponding proof. I just wonder, as teachers of math, and I teach computer science, or theories of computation, essentially mathematics, have we become too abstract in the way we present ideas nowadays, focusing too much on proof and abstraction and concept rather than introducing people to the visualization and the intuitive understanding first?
I don't know about that. I think that both have their place. And I think that for me, what's interesting is kind of the blend between the 2 types of thinking, kind of this using this visual way and a very abstract. And you can bring things to both of those through each other. So I think they're both useful. I tend to be more of a visual type of mathematician, and I get a lot out of talking to people who are less visual than I am and more, more constructive somehow in their proof. So yeah, I think it's a nice blend. Yeah.
Can I just follow up on that? If I'm understanding you correctly, maybe they're complementary or synergistic, but in terms of a gateway drug for, I'm thinking about JMU freshmen.
It depends. I mean, there's all sorts of different types of learning styles. So there are some kids that they look at that. So can we go back to that first slide with, some look at that and they say, so they look at this and they say, oh, this has to be true because I can verify it. So they'll say, what would we ask? We'd say, show that this thing equals this. That's how that's how a lot of people would think about this, verify that this is true. And not so much intuition about why it's true. But now, when you look at just this image, if you just have the image and you say, how's that image related to this thing? You don't even know what X and Y is in this thing. So just figuring that out, if you just plop down this figure, I would say in my classes, I would say that most students would much rather do this problem, do this proof, than try and figure out what's going on with this. This is a fairly high level of thinking. This is more kind of computation. So I think as we move them to kind of proof structure, I think things like this are really nice. And this isn't the only kind of technique, but getting intuition is useful. And I think it depends at what level you want to hit it. Yeah?
I had a question that sort of connects with this thread. And that is about the relationship between the real world and the world of mathematics. Because it seems like it seems like the beginning of mathematics was, and I just read a book about this, that up until sort of 17th, 18th century, all of this is about description, right? It's about describing. And up until that point, the description was about the world, right? You looked at the world and you described it. Mm-hmm. And you looked at the world that you saw and described it. So the Vitruvian Man is about describing something that you see out there. And that by the later 18th century, that link became uncoupled. And that instead of describing the world, you were describing things that one could not see. And so I'm wondering about, and it sounds like those are the two sort of modes that are being discussed here, that there's what you see and what you can imagine. And I'm wondering about the relationship between these two.
So, yeah, that's interesting. I think, so my take on that is, I think the more you do either of these things, the better you get at them. So by saying that mathematics is talking about maybe more things that we can't see. I mean, in the whole postmodern, I mean, a lot of art has started to talk about things also that we can't really visualize, these kind of crazy constructions. And for me, it's just, you're using these tools, and if we're thinking of mathematics as a tool in this way, that you get something out of both. I mean, that it's really people who do this high dimensional, I mean, I don't do high dimensional stuff, but I bet there's a ton of people in the department that could give you a really nice description of what is S3, what is the sphere in 4 dimensions. I'm sure there's a lot of people that could do that. I'm not one of them because I don't work in that area. But I think the more intuition you get about things, the easier it is to think in these kind of newer ways.
So in other words, the more you understand about the tools, the more you can apply them to things that do not exist visually.
Yeah, and bring things to areas that you thought you understood well. Like that Mobius transformation. I mean, people for years just thought about it as, you know, these convolution these maps moving all around. But until you really think about them as that visualization, it's not so coherent how to understand how changing that map changes the image. So yeah, I don't know. I mean, I think I like them both. Yeah, Dave.
Actually, I had a response today. Is that okay?
No.
You had a question about the relationship between the real world and the mathematical world. If it makes you feel any better, here's a quote from Einstein. How can it be that mathematics, after all a product of human thought, independent of experience, is so admirably adapted to the objects of reality?
Yeah. So it is truth, we think. And for me, it's the blend like that, like a bubble. I mean, that to me is kind of captures perfectly. It's this really difficult thing to talk about mathematically, but in nature it exists so beautifully.
That's physics.
It's math.
I would add to this with deference to the philosophers here, that sort of the classical view actually is that mathematics is the real world, and the crappy physical world that you're talking about is like this other little thing that happens to sort of.
Yeah, I mean, you couldn't do any of these constructions.
Yeah, it really wasn't until like Kepler and Copernicus and Galileo that the idea of applying mathematics to the empirical, the world of experience. You know, before that, it was like the abstract world of pure forms, the Pythagorean Platonic world. Mm-hmm. That was the real world.
And that was just to step you up to talk about the spheres, right? The harmonics of the spheres. So, yeah. Okay, good. Any other questions?
Students have questions. I can see 1, 2, 3, 4. I see all sorts of students here, and I have no doubt that one of them will soon raise their hands and ask a question.
Hey.
I'm really interested in seeing the wave ripple video.
Okay, we can click on that. That one's cool. So that's a simulated wave tank. We actually have a wave tank here that we haven't set up. So we're using the simulation. And I may have to go there and operate it. So it's the top link, that Volstad. That's an active link, Daniel, on the.
Across the top?
Yeah.
Yeah.
Click on that.
In the last browser's actually up.
Okay, there's a job applet. I don't know if it's popping up. There's a bunch of applets. This is a really cool physics site. The guy does a lot of coding, so he does really nice simulations. Well, so a Java window actually usually pops up in the background here. So maybe it's one of these. No. You may have to look at this on your own. But it's really interesting. You can set up all kinds of different sources, and you see the wave tank. You can put walls on and see the reflection come back. You can see tons of stuff with it.
It's a physical simulation?
You can, if you want to go to a web browser, yeah. It's a numerical simulation. Yes?
The people who are doing this with mathematical information and visual art, there are also people doing this with mathematical information and auditory things, like music.
Yeah.
Is there anyone who's doing music and visual? I mean, it seems to me that mathematics can be converted into those two.
Well, actually, that's another demo on this. This is actually, so they do the harmonics of the drum head.
At the same time.
They talk about the special functions, and you can click on the sounds. And actually, another one of these is the cornstarch. They actually play a speaker at a certain frequency, hertz, and you see all these patterns. You get really, really kind of nice wave patterns. Yeah.
CYMATICS, cymatics.
Uh-huh.
That's what you want to listen to.
Yeah. There's a video for this as well.
Oh, is that?
Yeah.
Roger, which one is the best one to choose?
I think the have you guys seen the ferrofluids before? Click on the ferrofluids, because this is phenomenal in such a creepy way.
They're actually using this in car braking.
Okay, so this is a track. This is what I understand this to be, at least. Oh. Here's part of a meat grinder. They put this down, and they're able to magnetize this. So you're able to kind of visualize. This is a fairly descriptive YouTube video. There's others that are more artistic. But I like this because it was quite descriptive. Maybe a little long-winded. Okay, here they're representing the field line. So they're able to change. So they're driving the system more magnetically. And they're able to now, so these are all these magnetic balls sticking from the edges, so along field lines. And then they're going to dial back the magnetic force. And they're going to watch how these things drop off. So they're measuring how the field line, the strength of the field lines, basically, by a differential type experiment. So they're starting to drop. So the field lines are tighter here where it's more compact. And Francoise, this is physics as well. Okay, so then they do this plot. But modeling this stuff is the... So now they're driving it. So now they're cranking up the charge. It pulls up the ferrofluid because the field lines were stronger at the top.
What is ferrofluid?
It looks to me like motor oil mixed with copier ink. I think, in fact, that's what it is. The toner.
Or
Just motor oil that's never been changed.
Yeah, from my car probably, full of little magnetic particles. But isn't this, to me, is so creepy looking? In a very organic, unnatural way.
I had one more question about
Uh-huh.
the.
And then put on the cornstarch one too, the speaker.
I had one more question about the 4D. You said you can fly through the 4D.
Well, you can fly through the 3D representation of the
4D.
3D projection of the 4D object.
What do you learn from doing that?
You can look at symmetries from different places in the. So you can look and turn around. It's like being in a star field, and you're looking for recognizable constellations. You're doing the same kind of thing. So this is cornstarch. This is a non-Newtonian.
Can we maybe get some sound on that so we can hear the...
It's kind of what it sounds like.
It's about 560 hertz.
Oh.
No, I mean, I don't know. That's probably close, though.
It's a new generation lava lamp.
Yeah. So, wait,
So this is shear thickening. You can look at, so, you know when you hit water when you're going really fast, it feels really hard? Well, the same thing's true with this, but it's even worse. The harder you hit it, the harder it gets.
Non-Newtonian solid.
Yeah. So, and you can actually do this with granular material as well. So you're getting this kind of behavior with a lot of media. So it hardens as you do it. So if you have a vat of it, and I was going to bring some, but I forgot. Do you have any in your office still? So you can have a vat of cornstarch, and you add some water, and a stir stick, and if you stir very slowly, you can stir it. But the faster you try and stir, the harder it gets to stir. You can see pictures on YouTube of people running across vats of cornstarch. When you run quickly, it acts like a solid. When you move slowly, it's like a liquid. So it's a very non-intuitive thing. Ketchup. Non-Newtonian fluids, if you have a vat of them and you spin them, and they're time reversible often, so you can spin them back and do all sorts of stuff.
Wait, can you explain that last part? They're time reversible?
So you can, if you have a vat of them, like a tub, and you drew a line of ink. So this classic image from the 50s. This guy's saying, and now we have a non-Newtonian fluid. We apply a dye line and turn on the phonograph. So they turn on the phonograph with a thing stuck in it. It's stuck to the side maybe, and the thing's spinning in the middle, or it's got a... Anyway, so it winds up like a spiral. And now we turn the phonograph in reverse. And they turn it back, and it comes back to the same perfect line. It's really cool. So things look the same forward yeah. So there's a lot of cool stuff. Smale's paradox. Check out, this is a real mathy thing. This is looks like a 3-lobe eversion or something. So you're plucking this thing. You can't pinch it at all. So you can push it through itself. So you have some non-physical rules, but you can't pinch it in any way. So we.
Paradox, Roger.
No, it seems like it should be, but it's from Smale. And actually, when he proved it, they thought his proof had to be wrong because it doesn't seem like you should do it. But mathematically, this is talking about a homotopy. It's moving one shape into another shape. And you have certain rules. One of the rules you have here is you can't puncture the surface. You can't rip the surface. But you can push the surface through itself, which is the non-intuitive rule. So you could imagine if you had a ball and you wanted to turn that ball inside out, you'd kind of want to just reach through it and grab it and yank it and pop the thing through. So that's what they're doing. They're pushing, they're pinching, they're sliding through. And there's a lot of visualizations of this. It's called a sphere eversion. So this is a 4-lobe eversion. So yeah, this stuff's cool. Differential topology. Okay. Well, thanks.